Okay, so today I'll be going over Project 4, Part 2. So this will be the 2D flow simulation over a semicircular cylinder with a diameter of 1 meter, free stream velocity of 30 meters per second, and density of air as 1.2 kilograms per meters cubed. This analysis will be steady, viscous, and turbulent using any turbulent model. I'll go over that as I'm doing the solution part of this. The length of the page is not necessary, so it is going to be a 2D simulation here. So we're going to start with going to our workbench here, opening up a fluid flow fluent case here. Set geometry to 2D because width is irrelevant. New design model or geometry. Let it open up. Now that it's open, we're going to go to the XY plane. Simply just look at XY plane here. Go to sketching. Easiest way to do this, I think, is starting with a circle. Start at the origin. Draw a circle. It's going to be in meters, so the unit should already be set to meters, so you should be fine there. After drawing the circle, you're going to draw a rectangle that basically encapsulates it. Now we're going to go to dimensions. As said in the project directions, it'll be 1 meter diameter. So we're going to go here, diameter 1 meter. You can make these generally whatever you feel, but I'm going to simply make the basically I'm going to make this triple the diameter, make this triple the height. And I'm going to make it, I'm going to make that 3 meters and then 9 meters. I'm going to lay some bias though, and basically make this distance horizontal distance from this edge to the center. I'm going to make this 4 meters, so it's 4 meters on the left, 5 meters on the right. And then once you're done with this, as you see, the circle's still there, so we have to go to modify right here, trim, and basically cut out these to make it the nice semicircular shape like this. At the end, you should have something similar looking like this. We're going to go to concept now, surface from sketches. Select our sketch, apply, and then generate. There you go. With this done, we can minimize this and open our mesh. Mesh is the important part here. We want to make sure our cylinder wall is well defined so that we actually get the force reports on the cylinder wall. There we go. The mesh is now loading up. The first thing we're going to want to do here once it loads is insert a new method for meshing, and we're going to use triangles this time. Here we are. We're going to go to our mesh, insert method. We're going to select the whole face, apply. We're going to go to triangle method. It's perfectly fine. Then we're going to go insert sizing here. Make sure you're on selection of edges here. Select this, apply. We're going to go to number of divisions here. You can play around with this. It'll show around the cylinder wall. You want this to be well defined. I find 100 to be pretty well. As you see, it's pretty finely set up here. Then down here, capture curvature, you're going to want to turn off and turn it to hard behavior. And then make sure blend to neighbors is also off. After this, you should be good. One last thing we're going to do is insert an inflation over the whole surface face. And we're going to put the inflation option as a first layer thickness, and the first layer height we're going to define as 0.03. With the boundary being the edge of the circle, the cylinder wall. All this other stuff you can keep the same. And then at the end here, we're going to generate this mesh. So if you look at the mesh, you can see it's generally, we're actually going to change this to, 0.2, just to get a little more finer of a mesh on the outside as well. Generate this once more. As you see, it's kind of finer mesh on the outside, but it's a really fine mesh approaching the cylinder wall. This is as we want. And after this, we're going to want to name sections. So you're going to want to click the top, hold Control, select these bottom two, name them. Name it symmetry, those. You can name this anything you want. Just make sure you know that it's the inlet. And name this something like outlet, so the program and you know it's the outlet. And lastly, we're going to name this cylinder wall. Once we have these named, we've basically done what we need to do in ANSYS, or you mean the meshing. You should have 4 named sections, triangles method, sizing around the cylinder, and then inflation. Minimize this, update our mesh right here before going into the setup here. We're going to use double precision to solve our processes. Start. Pretty basic generic stuff. Let this load. While this is loading, we're going to want to get the velocity contours with streamlines and then the pressure contours along the semicircular cylinder. That'll be 2 contours right there. Then we're going to want to plot the pressure coefficient and velocity distribution over the semicircular cylinder. ANSYS can plot these for you. You can also plot them in Excel. And then lastly, we're going to get the drag and lift coefficient, which we're going to use a force support to get those 2 for. Okay, so now that we're here, we're going to see that we have an inlet and we have an outlet right there. So we're going to go here to materials, fluid, double click on it. Air, I'm going to change this just to 1.2 as the project denoted. And then we're going to boundary conditions, inlet. Change this inlet velocity to be 30 meters per second. Apply. Close out of that. And then we're going to go to reference values here, just real quick. Compute from the inlet. And basically make sure the entire surface body is the same as the inlet, because we're only focused on the cylinder and not the entire area right here. We're going to make sure those are the same. Now that that's done, we can go to models here. Choose our viscous model. I'm going to do epsilon here. Okay. Now that those are set up, we can go down to initialization. Hybrid initialization, go ahead and initialize. And then we can go ahead and run calculation here. I'm going to do 200 iterations. Generally do a higher number, get better results here. Alright, now when that's done, we can go to graphics now. It wants the velocity contour, so we can go over here, contours, velocity, velocity magnitude. I'm going to choose the surface body and the cylinder wall. As you see here, the velocity will reach its max right at the top of the cylinder, as seen in class, and then it will drop into the wake region here. And along the wall here, it'll be 0 because we're doing a viscous analysis. So we can go ahead and get this, but it wants the streamlines as well. So what we can do here now is go to path lines, style line, do 1,000 steps. And then what we're going to do here is go to select the interior surface body. Sorry. Select the inlet. There we go. And then you'll see the streamlines here. Once we save display this, it'll be saved right here. We're going to go back to our contour. Just right click display. And then right here, we're going to go to add to the contours. And then here you go. You'll have the streamlines overlaid on the path line, sorry. Okay, streamlines overlaid onto the contour. I believe we also need the pressure contours. So it'll be 3 contours for the pressure. So we can go back to contours here. Just do static. I'm just going to name it static for static pressure. Again, I'm going to select these 2. As you'll see, the static pressure is highest on the top, or sorry, lowest on the top, because that's where the velocity goes to the max. And then obviously we'll have static pressure, and then you'll have dynamic pressure here, and then you will have total pressure. And as you see, for example, in dynamic pressure, aligned with theoretical, the dynamic pressure will be highest on the top because that's where the velocity will be the highest. So you should expect the highest dynamic pressure up there. I believe that is the contours we needed. And now we want to plot the pressure coefficient and the velocity distribution over the surface of the semicircular cylinder. So what we can do here is now go to plots, x, y plot. We can just go to pressure. Go ahead and select pressure coefficient. Only select cylinder wall here because we want the plot over the cylinder wall. It looks something like this. And then the velocity over the cylinder wall again. This should be 0 because it is a viscous effect. So the velocity along the surface should be 0 because of the no slip conditions. So now that we have these two plots, the last thing we need to get is the drag and lift coefficient for the semicircular cylinder, and then tabulate it. You can do that in Excel or just create a table in Word or Google Docs, whatever you're using. So here we're going to go to report definitions, open it up. We're going to create a new force report drag. You can just name this drag coef. Name it drag coefficient along the cylinder wall. Compute. You'll see here we'll have our drag coefficient along the wall, right there. And then what we're going to do is we're going to go create a new one of these. So we can hit OK. And we're going to create a new force report lift along the cylinder wall. Compute it. That will be our lift coefficient. OK. Close. Another way to get the drag coefficient would be to go down here to reports and forces down here. Cylinder wall, forces, print. And you will see your various coefficients here. This will give you your actual forces in newtons, and then it will give you your coefficients of pressure and viscous drags, and the total drag coefficient here as well. I believe that should be everything for project for part 2. We did the steady, viscous, turbulent analysis. We got the drag and lift coefficients. And then we got the pressure coefficient and velocity distribution on plots and the contours. So yep, that'll be everything. That's it for part 2.